In section 2.2, we're going to inspect a little bit more about analytical geometry behind the derivative. So we'll start off with some vocab and definitions. We're looking at a function, f, being differentiable. And if I can help you with that. Differentiable is the ability to take the derivative of. So if we're going to speak about it in two ways in this section. So can we take the derivative of this function? So it's differentiable at x equals a if the derivative at a exists. And remember, when we use exist in a sentence, what we're trying to specify is that your derivative at the certain point is a real number. Remember how we talked about infinity? It's a number, but we don't consider it to be real. So technically limits at infinity don't exist. It's kind of the same idea. So now we talk about what happens in terms of an interval. A function f is differentiable on the interval a, b, if the derivative at every value in between a and b exists. And one more time, it kind of sometimes to give you an idea, if we want to speak about differentiable, one of the kind of the key notes, if you're viewing the graph, if you are differentiable, you are a continuous and smooth function. So that's kind of going to be a nice visual for these types of problems. So if I could help you with giving you what happens when a function is not differentiable, sometimes that helps us figure out how to look at functions in different ways. So we're going to talk about what happens if a function is not continuous at x equals a. Sometimes they say discontinuous. I'll just say not continuous. So I'll draw a few examples so we can see. We've seen some of these in our previous problems before when we were dealing with continuity. You know, sometimes we have an issue. We have a nice function, it's smooth everywhere, but there's a hole and then there's a point where it jumps to. So that could be an example. We also have an issue of the function. I think I drew a on the positive side of the x-axis, but it could be anywhere. We could have an issue where we have a function that's piecewise. And there's that jump discontinuity coming in again. And then we have the infinite case or infinite discontinuity. That would be the case if, let's say, we had ourselves a vertical asymptote at x equals a. So some of the samples that we were dealing with in section, I think it's 1.8. So we know at x equals a, if we run into any of those cases, you can't take the derivative of the function at that particular point. So another way, sometimes you run into cases where your function f, we call it like a corner. So I'll say it that way. If f has a corner at x equals a, and remember, if we're differentiable, we're supposed to be continuous and smooth. If you have a corner, it kind of signifies an abrupt change. And if derivative is a rate of change, you can't just change right away into going from one speed to another. There's always like a rate, a constant rate that you're taking. So some of the cases of functions you've seen before, maybe we have the case of an absolute value function. That's a prime example of a corner. All right, sometimes we run into, maybe it takes a certain behavior, a little smooth, but we do have a dip, little corner there. So it looks like all the functions I've been drawing are continuous, and most of the parts are smooth, but there's always a place where there's an abrupt change. So that we'd have some cases of not being able to be differentiable there. Now, one last way we could run into the case of not being differentiable, we may run into functions that are smooth, they're continuous, but we have ourselves a vertical tangent line at a certain point. Let's see if I can draw that the best I can. So we have f, I'll write that down, has a vertical tangent at the point. So we might run into a case where we see, let's see that vertical tangent line. Let's see at x equals a, if you were trying to calculate their derivative and you get something that's undefined, vertical tangent. And in other cases, this is a little hard to draw, but maybe we'll let Desmos. We have cases that look kind of like S's, but they're very vertical. So we may have a case of a vertical tangent line at one of these points because it only goes through that part. So I'll leave that for you to play with. So all this is leading up to trying to understand how the derivative describes the behavior of the actual function itself. So we're looking into, what is the derivative telling us about the original function? And some of these we can kind of see if I, let's see if I can share one of the screens with you with one of our Desmos. Let's switch over. Let's do one of the slopes of the tangent lines. Okay, so this is also located in your section lecture note pages. But we can kind of see the function. It's quite complicated. It's in blue. And what we have in the red is the calculation of the tangent line. So if we're looking at the tangent at particular points, you could push play. And then it kind of shows you what's happening to the tangent at all the different points from -10 to +10. So you can kind of see tangent ends up having positive slopes, negative slopes. Sometimes, I'll pause it for a second, sometimes you run into a tangent with a 0 slope. This would be a tangent that has a negative slope. You can kind of inspect as you go along the way. We have a tangent, I believe that's a 0 slope, if I can get that steady. Tangent with a positive slope. And you can kind of see what's happening along the way. I like to think about that as a little surfboard, kind of riding the wave of your function. And the angle at which the surfboard's making gives you, or the slope at which the surfboard is making tells you what's happening with the slope at any given time. So if we kind of play with, what's happening when the slope is 0, what's talking about what is happening in the function. When the slope of the tangent line is negative, what is the function doing? And when the slope of the tangent line is positive, what is the function doing? Well, we have that answer for you. And definitely we can inspect this with a lot of different functions. But we kind of ran into the fact that if we had one of the functions, and I'll kind of draw maybe a piece of the function. So we had f somehow dealing with this. I know that looks like a corner. What am I doing? So we have some sort of function f. If your derivative is positive, again, greater than 0 meaning positive, that would be a case if you're at a point and then your derivative has a positive slope. Lots of different ways along the line. Even right here, we have a little bit less steep of a slope. But what that tells you about the function is that the function, for every x value as you increase, the y values are also increasing as well. So this is the definition of what it means to be an increasing function. Now, if we look at the case of what's happening if we have a negative derivative. So if I pick a point on the function and I'm drawing a mini version of the tangent line, looks like the slope is decreasing from left to right. We can go a little lower. We can kind of see that sometimes, it might not be decreasing at the same rate, but we do see that whenever we have a slope or the tangent line has a negative slope, that means the derivative at that point is negative. So that would imply that our function is decreasing for those values of x. And if you're decreasing, remember, as the x values get larger, the y values get smaller. Then one of the key points to separate the increasing versus decreasing, if you had a case of your derivative having a 0 slope, so that would be a case of running into a horizontal line for your tangent line. That's giving you the case, well, horizontal lines are constant. So we would say that the function is constant wherever the derivative is 0. And so remember, if we're looking at this idea of what does the derivative tell us about the function, we're kind of asking ourselves the questions, where is the derivative negative? Where is it positive? Where is it equal to 0? So we're looking at characteristics of your derivative to give you information about the corresponding relationship to the function f. So we have to be really careful. I don't want you to confuse, little caution symbol there. Be careful not to confuse positive and negative with increasing and decreasing. Remember, we're talking about what's happening with the derivative versus its function itself. So it's true that a function, you can be a negative function. Okay, so let me see if I can write this in plain words. Be careful. Wow. Yes, even Leica says be careful. So be careful not to confuse a positive and negative function with increasing and decreasing. So it's case that, a function, you can be negative and still be increasing. So let me see if I can, like a quick example off the top of my head. You could have a case where your function, I'll do something like this. Looks like if you were to calculate slopes of the tangent lines along, for a certain part, maybe the left side, maybe all up until whatever this value would be. I'll kind of separate that. But everyone left to the orange line, we have a case of a function that's increasing, but the actual y values of that function happen to be negative. So that's what we're trying to get over here. So we are going to do a lot of comparisons and seeing if we can figure out what the graph is doing and what the graph of the derivative itself would be doing. This is going to be quite interesting. So, example 1, it's got about a lot of different parts we're going to explore. Functions will get increasingly more complicated. Given the graph of f, they want us to sketch the graph of the derivative. And we're going to use, very excited over here, yes. We're going to use the idea of kind of calculating, when do you see a zero slope? When do you see a positive slope? When do you see a negative slope? It could give us a better idea of what we're looking for. So I'm going to start off with the way I like to play with these and draw these, especially when it comes to WebAssign and judging. I like to always draw the original function on top and then the corresponding derivative right below, so I could kind of compare particular x value points. So for part A, we're going to start off with a constant function. I'll do my best to draw a straight line for you all. So constant functions, horizontal line. F is constant. I'll say maybe I'll give you a little bit more information. F is constant. Now, when you're looking at a constant function and you're trying to look at points along the way and calculate the slope at certain points, slope of the tangent line at certain points, in all cases, the slope is equal to 0. So if we were looking at what should we be doing to draw our derivative, this is a number that's associated with our derivative at every single point. If we are looking at graphing our derivative, we have, I'll do this in green maybe. If the derivative is equal to 0 everywhere, that is a horizontal line, otherwise known as the x-axis. Do my best to draw those straight lines as possible as I can. But this would be the graph of your derivative. Remember, it's equal to 0. So we'll play a little bit more, get a little more exciting. Let's suppose we have f being a line with the slope 1. Let's write that 1 a little nicer. So I can pick anything as long as the slope is 1. I'll pick something nice where maybe try to get it going through the origin. So I'll draw something like this. A little shaky on the edges, just pretend those are a line for you. We have our f. Now, again, we're interpreting derivative as the slope of the tangent point or tangent line at any given point. So if the slope is 1, then our derivative itself, every time you calculate it, the derivative itself is always going to be 1. So that would be the case of a horizontal line. It's constant the entire time. We have our case, so I'll draw this maybe at 1, horizontal line through y equals 1. So that would be the graph of our derivative. So now, let's look at this a little bit more. What happens? I'll sketch these out for you. Let's suppose, I'm going to do something with corners, but I want to make it neater. So let me see if I can do, let's make tick marks out to +2, tick marks out to -2, maybe in both directions, x axis, y-axis, the best we can. And let's say, let's go through the origin. Maybe I'll have it at -2, 2, and 2, -2. What I'm interested in, I'm going to make corners. So let's draw a horizontal line kind of there. I'm going to connect my points here the best I can, and something over here. There we go. So there we have it. We have f, a function that has some corners. Now, generally when you see corners or jumps, we end up having a piecewise function. Kind of mark those there. And if you remember, when we are looking at the derivative, if you have corners, you do not exist at that value, so you're undefined. Maybe I shouldn't say undefined, you just don't exist. Let me see if I could also break this up. So once you kind of figure out where derivatives don't exist, where the derivative's 0, you can break the x-axis up into a few different regions. It's kind of how I like to look at it. So I will take my graph below. I'm going to set myself up for drawing the derivative as a function, and I'll just kind of correspond, you know, the same distances I took for the tick marks on the function. I'm going to correspond those. So I have +2, -2, doing the best I can. And we still had positive and -2 as well when we were marking them earlier. Now, what I like to do, and this is kind of, maybe you can kind of lightly go through this, the minute you see something that has a derivative that doesn't exist or there's issues, you can break your x-axis up. And so I kind of, you'll see how the reason why I drew these points or these graphs right under each other, I can remind myself, I'm doing this very light because I know that's not really part of the graph, but it does help me see the key points in the derivative. Where the derivative, we had some issues where we had a corner, abrupt change here. It breaks the function up into 3 pieces. And if you could kind of inspect the slope along each piece, you could have an idea of what the derivative is doing. So first off, if I'm looking at the left part of the function, I do have myself a constant function. See if I can highlight it, and I'll go with yellow. And if we want to talk about the slope on that piece, the slope here of a horizontal line is always 0. So that's going to tell us for all the x values up until -2, where it's undefined, that might be a good place to put an open circle. We should have the derivative being graphed as y = 0 along that piece. Now, similarly, if you look at the horizontal line for x values to the right of 2, here the slope is also 0. Slope of the tangent, a line at any point. And so similarly, at x = +2, where we're still undefined, we're going to have ourselves the derivative equaling 0, or the function being 0. So I need to inspect what's happening, or what's happening with the slope for all the x values in between -2 and +2. And so we want it to be a little bit more accurate here, so we took it. If I can calculate the slope by calculating rise over run from one point to the other, I'll write it down. I'll go from our origin. I can say the slope is down 2, right 2. So down to right 2 ends up being simplified to -1. So for every point along this piece of the function, your slope is always -1 anytime you could calculate the slope of the tangent line. So that's going to tell us that the derivative part, the derivative would be graphed as y equals 1. Excuse me, it should be -1. Let's write that down a little more carefully. So that would leave us with constant derivative. It's a horizontal line, but again, we're not defined at those corners, -2 and +2, so we end up having open circles as well. So if I could kind of go back just so that we can see one more time. The slope of every point on the line or piece of the function corresponds to what type of graph your derivative will be. So if we look at the left side of the graph one more time, the slope is 0. So if you were to graph y equals 0, we wouldn't really call it y because we're not looking at the function. We are looking at the derivative being equal to 0. Same story on the right side or the right piece. In the middle, the slope of the original function, every point on that piece ended up being -1. So the derivative would graph as y equals -1, although we don't necessarily call it y, we're calling it f prime, just to help you kind of see the difference. So we have the original function on top, the corresponding graph of its derivative below. Let's take this a little bit more. Let's give ourselves a parabola. Nice little y equals x squared. So, let me see if I can mark this a little nicer. Be clear about this. We have going to -1, 2. You can go to 3 if you'd like. 1, 2, 3. 1, 2, 3, 4. Just try to be as uniform as possible, or if you end up having some graph paper like we do on this side, that could work too. But let's see, if I have my parabola and I want to graph some points along the way, I'll say f of x equals x squared. We know 0, 0 would be a good candidate, -1, +1, 1, +1, 2, 4, all points on this parabola. So we can graph as accurately as possible. And pretty much what you'd like to do is you want to picture tangent lines at all the different points, but we can picture them on the points we actually use to calculate. So if we were to draw a tangent line, that would be a tangent line that has a negative slope, a tangent line at x equals -1, a little less shallow, but it's something with a negative slope. Maybe a tangent line at x equals 0, horizontal. Tangent line at x equals 1. We see that we are rising from left to right, positive tangent. And same thing, we have ourselves a positive tangent. Now you can expect more points along the way if you prefer, or do all the calculations. We had a problem from the last section that had us calculate the slope of the tangent line to any point on the y equals x squared. So you can play around and see why we're getting those values, but we can also use the fact that wherever the derivative is 0, we can use that to separate our x values up, or our x-axis up. So I'm seeing it right here. At this point, only at one point, our derivative is 0 right here. So slope of the tangent line is equal to 0 at x equals 0. So that translates down to the origin. We know we would have a point there. So it's a singular derivative. Now we can separate the coordinate system, or the axes, up into two pieces, left side of the 0, right side of the 0. I would still recommend writing in your corresponding pieces. And I like to use the same scale I use from my original function as much as I can. And so here I'd like to really see, for all the x values on the left of my x equals 0, I'd like to inspect what's happening with the derivatives. So if I calculated a few more of them and drew them in, yeah, the derivatives, the slopes are getting, they're coming from really steep to not so steep. But in all cases, the derivative is negative. So negative is another way to talk about less than 0. So maybe if this helps you, you could write in English. You have negative slopes on the left of x equals 0. And probably guessing, if you look at what's happening to the right of x equals 0, we draw more slopes in, or more tangent lines in, we're ending up with positive slopes. So that would imply that we're going to have our derivative be positive numbers greater than 0. So how does this translate to the graph? We're looking at what to graph as a y equals. So if we do this, if I was interpreting this, on the left, f prime 0, that means that your function should be below the x-axis. So we know we have a negative. And if we end up having f prime 0 be greater than 0, and I should actually write this down for you. Why am I doing this verbally? So this would mean that our function, when we graph it, f prime graphs above the x-axis. And one more time, less than 0 means f prime is below the x-axis. Now we can play around. I believe we already calculated the slope of the line at x equals 2, but we could play around. If I'm trying to play, if I'm going through this, I should get f of x equals 2x, or the derivative is 2x. So if I can graph that, up 1 over 2, down 1 over 2, we end up having the graph of our derivative. So if we can kind of see if this works out. And by the way, we might be able to inspect this a little bit more, but we will learn if we are calculating the derivative through the limit definition. So just so that you know, I didn't come up with this out of thin air. Maybe drawing on examples from the last section, looking at calculating the derivative based on the limit definition. That was when we were doing the f of x plus h minus f of x over h. We ended up getting 2x. So if I were to draw that in, I just want to inspect that, yeah, if I know at x equals 0, if we were doing the graph, we have the derivative crossing through 0. All values to the left of x equals 0 end up being negative. All values to the right of x equals 0 are positive. So we have negative slopes coming from the function translates to the graph of the derivative being below the x-axis, and positive slopes from the function itself translates to the graph having positive x values, positive y values, meaning you have graph above the x-axis. That's a lot there. That's quite confusing. Take some time to play with that. Not too much time because we're moving on, but you could always stop and rewind. That's the good thing about watching these videos. So what's happening here? We're going to look at, let's do something like a trig-like function. Some cases. So let me see if I can draw this out. 1, 2, 3. 1, 2, 3. 1, 2. Let's do this way. Okay, so I'm going to have a minimum point, a point crossing through the origin, and then we'll go here. 1, 2, point here. And the way I kind of want to play with it is I want to see a kind of a wave going on. Maybe not so much that way. Tried to make it as symmetric as I could. Let's see. All right, that's good enough for the most part. And actually, let's see if I can do this. That should have been drawn on the other axis. So let's see if we can move that up there quite nicely. There we go. Remember, we're starting off with our function and we want to draw the corresponding derivative. So my piece of advice, I'd like you to start maybe marking where your function itself has a 0 tangent line. So let's mark where our derivative would be 0. So start looking at slopes of tangent lines all the way through your function. You're going to find that once you hit maxes and mins of the functions, or they say high points or low points, that's going to help you with determining regions for your x-axis. So that's really key here. So it looks like at x equals -3, so I'll try to draw my tick marks in relation. The derivative itself actually has a 0 slope, so I would mark a point there. And also at x equals +3, see if I can get that to line up right on top. So I can say, when I break up the x-axis, I should have a 0 slope for that tangent line, which means the derivative is 0. Now, what you'd want to do is try to determine, well, where do you have positive slopes? Where do you have negative slopes once you've been dealing with where the slope is 0? So you can pick points along the way and test them as you go and say, oh yeah, every time I draw a point and a tangent line to that point, it appears that I should have positive slopes all the way up until x equals -3. So that would imply that my derivative should be greater than 0 at that point. Now they kind of work inversely. You can play around with this, but I'm gonna wait before I go through this. If I look in between -3 and +3, and I try to calculate a bunch of slopes, in all cases, even at 0, it looks like we're having negative slopes for these derivatives at these points. So that's going to imply that our derivative is negative. When we graph it, it should be below the x-axis. Similarly, move on over, and it looks like no matter what we do, we are getting ourselves positive slopes for x values from 3 and beyond, not including 3 because that's where the derivative is 0. So I kind of like to mark myself a little note to kind of remind myself. The derivative should be 0 at the x equals +3, x equals -3, and then along the regions, the derivative is greater than 0 on the two edges and less than 0. So if we kind of play with this a little bit, if you're trying to make things smooth, and we'll get the hang of this, if the slopes are negative and they're getting increasingly less shallow until we get to x equals 0, it appears that our derivative is going to look something like such. Because remember, we have to be above the x-axis on the two edges, below the x-axis in the middle of the 3, -3 and +3. Now you might not know how low to make that value. You could do a calculation, see what happens. But in all cases, you would get the idea of what your derivative is doing. So we'll find out a little bit more of the relationships. Sometimes when you start calculating derivatives using the differentiation formulas, you start to see like, oh, that's the way it is. But hang in there. Take time with this. This is difficult stuff. Analytical thinking or looking at things geometrically is not straightforward. So it does take a lot of practice. Got to really think about these things. Speaking of practice, let's do one more of these types of problems. Let's try maybe a more complicated polynomial. And I won't pick certain x values. I'll just kind of make it, I'll see if I can draw nicer for you. Something with a max, a min, and maybe a higher max. Local max, local mins there going on. And usually when I see continuous functions being drawn, I always look straight for where you have mins and maxes, local mins, local maxes, because that's going to give you a heads up according to where your derivative should be 0. If we were to draw tangent lines at these particular values, we would get the derivative to be equal to 0. So I'll mark these on the x-axis. Again, we're marking where the derivative is 0. Sometimes what you'll see me do is I'll go down and draw some faint lines so I can actually see the exact places. So it seems to be that we have a separation of the x-axis. Separates it up into a few more pieces. So as soon as you know where f prime is equal to 0, you can mark it on the graph of the derivative. I should label these so that we see them one more time. So I'll label them in red or mark them in red. Now what we want to do is go through each region, and I'll alternate them just so that we can see and inspect them. So if I look at the region to the far left, the yellow region for all the x values, if I were to look at all their slopes, it appears no matter what we do, and when we draw the slopes, we should have something that has a positive slope. So this is where we would mark f prime is greater than 0, or on your line, you can say positive slopes if this helps you. Sometimes writing English a lot better. So that means your graph should be above the x-axis somewhere. And if it's smooth, it should kind of follow the same smoothness as what you see above. The teal region, if we look at this a little more carefully, the teal region, if we were to inspect points along the way and their corresponding derivatives, we would have ourselves negative slopes. Sorry, I had to squeeze that in there, but that would imply that our derivative is less than 0. Now, alternating a little bit more, the next region over, if you want to play again, we see that we have some positive slopes all the way through. So if that's positive slopes, that means our derivative should be above the x-axis at this point. And then at the far right, all the x values from here on out, if we inspect the slopes at particular points or all points along the way, we are getting negative slopes. Sometimes you see me I like to notate things in English to help me see the math behind it. So that's going to give me the derivative should be below the x-axis. So sometimes what I'll do is I'll take the edges and I notice, it's going to be quite colorful here, but if I know I'm going on and on forever in the negative infinity direction on the y, and I'm supposed to be the other way around, so there's a little bit of an inverse relationship, kind of a mirror image in a sense. Maybe not mirror. I have to think about the wording on that. But what I would then say is, okay, looks like our function for the region, far left, all the x values, we should have positive derivative graph. We should have to go below the x-axis. And if we have to go above the x-axis in the next region, you probably have to do some sort of loop to get there. So the next region has to be above the x-axis. But if we have to, or we notice that we have to go back down below, there's a lot of drawing here where we're going to have to say, okay, figure out a way to cross back through and down. And so that would be kind of the idea of how are we graphing our derivative if we know the graph of the original function. I would like to point out these pieces right here and right here. If you wanted to be more accurate, you'd have to actually calculate the slopes of those calculate the derivative of the function at those x values to get how high or how low should you make those. But right now we're giving ourselves a rough sketch. This is something that can't really be done with a calculator. Please look at I do have a few things on the Desmos. Please kind of play around with them where you can look at the original function and see what the graph of the derivative looks like. They're not straightforward functions, so it kind of gives you a chance to explore a little bit. So stick with it. Maybe if you practice, a few of these, maybe a couple every day, you start to see the hang of it. You'll have a chance to demonstrate in WebAssign, although I know you pick from different graphs. But go again with kind of giving yourself marking different regions so that you know where you have positive slopes and negative slopes, and I think you'll do quite well. So just kind of a little bit more in-depth thinking. This is all theory here. There's really no concrete numbers we're plugging in. But if we're looking at example 2, I'll kind of play around. We're going to let the function f be defined for all real numbers and differentiable everywhere. They want us to sketch a possible graph of f that satisfies the given conditions. Excuse me, it's getting late. So let's remind ourselves, if we are differentiable everywhere, That's going to give us hints about the graph being smooth and continuous, no corners. The other thing I want to kind of play with is read my notation. I am reading f of x is greater than 0. What I'd have to say is the function itself. So f should be above the x-axis, positive y values, and it should never touch or fall below the x-axis based on that statement. The other thing I want to point out is if we look at this second condition, if the derivative is greater than 0, that's going to tell us that the function f is always increasing. Because they're saying for all x. And if you have the function increasing all the time, that means the slopes of the tangents are always positive. So if the function itself is always increasing, the slopes of the tangent lines are always positive, we're going to have to play around with what would work. Now, this is not an easy thing to do. Sometimes you picture the function and it works right away, but the majority of the time you end up trying a few chances and then trying to maybe justify why does it work or why doesn't it work. So I could kind of start off with, okay, let's start off with something, and I'll have the final answer in a second, but a few thoughts or guesses. Don't be afraid to be wrong. Guess on paper first, and you can modify your results. So I'm just thinking something that's smooth and continuous everywhere based on that definition. One of my favorite functions that's smooth and continuous could be the parabola. But if it's saying it's always greater than 0, that means it's always above the x-axis. I could start off with, okay, let's try that. And so you can say, well, okay, it satisfies part A, or well, the criteria for the first part, but you want it to always be increasing everywhere. When we look at the parabola itself, we do have a case where the derivative 0, it's only increasing on one part. So this won't work. Nope. And the reason why it's not increasing everywhere. So you try something, then you justify against it. Maybe that's not working. So let's try one more time. See, smooth and continuous. I always try really nice functions first. Don't make your life complicated. Smooth, continuous, something that's always increasing. I know a line with the positive slope's always increasing. That's another guess. And that's going to satisfy, this time around, it satisfies the second criteria. Function's always increasing. The slope of all the tangent lines would be positive. But it gives us issues with the fact that we are not always above the x-axis. In fact, if you look at all the y values down here, that's the issue. So again, this is another nope. The reason why is it drops below the x-axis. Now, let's see, keep trying. I was like, well, I'd be happy. I'd be really, really happy if I can maybe build. Let's see if I can build on what I just kind of figured out is maybe if I want it to always be increasing everywhere, why can't I do something where I make it a positive slope all the time, but maybe I stop. So maybe I do something like this. and go this way. And I can say, okay, we'll play. Are we always above the x-axis? Yes, all times. Are we increasing for all values of x? Well, we're increasing, we're always positive, we don't drop below the x-axis, but then we run into the case of for all x. Darn it, we're almost there. Our problem with our third guess is that we were not defined for all x. That was a criteria. So we could kind of go back and look through your catalog of your favorite functions. And one possibility, it's not always the final answer. I do know from my past that there's something with exponential functions. Some of them are always increasing. So I can look at something that looks like this and just ask myself the question one more time. Now, probably when I was first learning this, I believe it probably took me 20 or so times to get here. But we have to shorten our lecture. We can't have you sitting here 5 hours while I figure this out. But after you work with a lot of functions, you start to see patterns. And so, at this stage in my math life, I kind of know what works because I've seen different functions and I'm more comfortable with it. So just kind of give yourself time on this. But this would be a case that works because your function is always above the x-axis. What was that, Leica? She was not happy with that, but okay. So one more time, it is true. I don't know why she's disagreeing, but the function's always above the x-axis at all times. And the function is always increasing. You take particular points along the way and you calculate their corresponding derivatives, you're always going to get positive slopes. So this would be a possible graph that could work to satisfy these criteria. Let's try a couple more times and maybe I'll just kind of go with you. We could kind of go with what we answered. Sometimes that gives you a hint later. Just want to make sure when you're doing these types of problems, just be comfortable with making your mistakes. Don't always wait for someone to show you the way. Trying all this guesses helps us figure out the answers. And even if we're not making progress with part A, sometimes it could give you some hints to part B or different problems along the way. So hang in there. If I was trying to create a function, here I am again, I'm looking at the function always being above the x-axis for part B. Okay, so function above x-axis. And this time, it's a little opposite, it's always decreasing. So that would kind of make sure that the slopes of the tangent lines have to be negative. Well, sometimes when you have an aha moment on one problem, it gives you a better idea of how to approach the next problem. If I'm looking for something that's always decreasing, that exponential function kind of comes back to mind. But how I would have to draw it, if I was doing a possible sketch, I have to make it kind of decreasing from left to right. So this would be the case, something like that. You kind of wanted to test these on your TI also to play with it. A lot of times you would say, well, what if f of x was like 1/2 to the x power? That's kind of going to give you an idea. And that, my friends, does satisfy. If you were to look at slopes of tangent lines along the way for every single point, it looks like they're all going to be negative. So there's your answer for that. Also, just, to be honest, it would have taken me a lot longer. But sometimes knowing an answer to something else leads me to a faster route here. So one last one just to kind of play with and, make these up, see what works. Right away, I'm starting to get the hang of this part. It's kind of telling me, well, if the derivative is always, oh, excuse me, write this down. If the derivative is positive for all values of x, that means the function is always increasing. And so maybe those exponential functions come back, maybe I know, okay, maybe it's got to be something like this if we're always increasing. But they are specific, a little more specific. They want to tell us that the function itself has to always be less than 2. So maybe I can draw that on my graph. So that's your y equals 2, or your function. So you want it to be below that line, sort of like a horizontal asymptote. And you want the function value, when x equals 1, you want it to be 1. So you want 1, 1 to be on your graph. So we can draw that. We can see if that works. 1, 1. Draw that right there. So, I mean, I originally thought something from part A would work out. It's always increasing, but maybe I'm just looking at it the other way around. If I tried to make it always increasing, I notice if I run it this way, I'm going to actually end up going above y equals 2. So sometimes I can play with the reflection. We got erasers, change our minds. So maybe we can draw the function itself. Let's work with, it's always increasing. It's got to pass through this point, but it's always below the line. It looks like y equals 2 is working as a horizontal asymptote. I'll draw the exponential this way. So this might be a case where there's a reflection. But these are very valuable, very good for the brain. A lot of times it's painful though. It's not where you're going to get an answer right away. But the more you struggle, the better you get. So I just encourage you to stick with it. Try a few things, see what works. And while you're practicing, I'll see you in the next section.